Okay, class. Today we are going to I'm going to get back to soil classification. So a number of classification systems exist to describe the various types of soil in nature. So the purpose of a classification system is to be able to identify soil which has similar characteristics, similar properties, similar behavior, and loading. So this system must be based on a scientific system. A scientific method, should be simple. Permit classification by visual and manual test. Manual test is that to be able to identify soil manually. For instance, for a fine-grained soil, which has some plasticity, which has some significant cleanliness, cementite or multimolonite, it can be molded. So that if you can mold that soil, you can be able to tell the different. You can be told that this soil is coarse, fine-grained, or it has the fine-grained which has some clay minerals in it, and it should be acceptable to all engineers. So basically, we are going to look at a number of classification systems, which is AASHTO, which is mainly based for used for highways to be able to tell to classify or to name a soil of similar properties, physical properties. Then you have the unified soil classification system. Normally, this is used for foundation. Then also we have the Casagrande, but the Casagrande extended classification system was used to develop the unified soil classification system. So we are going to start with the American Association of Highway official system. This one normally is used for classification of soil for road construction. Normally, a road, as you know it has a number of layers. It has a wearing course. For that, it will have the base course. This is the road base course, the road bed. So it's the road base, Then it will have the sub base. Finally, it will have the subgrade, which also comprises of the subgrade. So such layers of soil, this material, the sub-base material should be of given properties, i.e., it should not be highly expansive in nature, and also should be a material which is of good quality in terms of particles, so could be able to offer some strength. But there we go, the better the quality we need. For instance, the sub-base should be of higher quality compared to the subgrade, and the load base should be of higher quality compared to the subbase. So this material should be of low plasticity. Why should it be of low plasticity? As we shall discover in our chapter 4, that the strength of the material is influenced by the water which is held by that material. So for instance, if you have a material which has high water, and the effective stress or the load carrying stress of the material is equal to the total stress minus pure water pressure. So the higher the amount of water, the more the effective stress or the ability of the material to carry load reduces. So that's why this material, since it is a layer which is nearing the wearing course, therefore it is a layer which should be of higher ability to dissipate or to carry loading. So then I will say that the actual soil classification system is used to determine the stability of soil for earthworks, embankment, and road bed, what we call the subgrade. Subgrade is a natural material below a constructed pavement, what we call the road bed. A layer of soil above the subgrade is called the subbase, and the layer of soil above the subbase, which offers high stability to distribution of wheel load, is what we call the base, the road base. So this road base material should be of higher quality compared to this. This material should, with the subbase material, should be a material which has ability. Sometimes it should have ability to drain water. So it can be designed as a filter layer or can be designed as a construction work platform. depending on the requirement of a layer. But if it's near the waterlogged places, they can be designed as well as a drainage layer. So should be coarse enough to prevent. It should be fine enough to prevent ingress of material from the subgrade, but also should be coarse enough to allow water to pass through it or to drain through it. So for actual calculation, we have three boundary steps we use. And this is sieve number 200, almost 75 micrometer. We have sieve number 40, which is 4 to 5 micrometer, and also 2. So the first sieve we normally use is a 200, sieve number 200. So if we can use a table, so normally this sieve is a which help us to differentiate if a coarse is coarse grain material or a fine grain material. So if more than 35% passes this sieve number, then the material is fine grain material. If less than 35% passes sieve number 200, or say 0.075 millimeter on micrometer, then that soil is what? Is a coarse grained soil. That's a boundary. So if you can look at this table, is as you can now, these are micrometer. These are micrometers. Micrometers not as considered our table B for B. So if you look at this table, now if I say that the coarse material, the material is divided using AASHTO into granular soil, coarse grained, and silty soil or fine grained material. Which sieve do you use? Sieve number 200. This sieve number. This number, sieve number 200. Is that okay? So when a material more than 35% passes sieve, it is fine. If less than, it is coarse. But if the coarse, we have A1 material, A3 material, and A2 material. So how do you differentiate between A2, A3, and A2? For example, if a material is coarse, it means that more than 35% is less than 35% has passed sieve number 200. Is that okay? Then and that soil is non-plastic. If you can say the plasticity index here, you find that it's non-plastic. It has fines which are non-plastic. Is that okay? That material is F3. But if the material is plastic and that plasticity is less than 6, then the plasticity is less than 6, then the material is an A1 material. But if that is more than 6, for instance, if the minimum is 10, the high plastic liquid limit. So if the minimum is 11 or the maximum is 10, between is more than 6 but less than 10 or equal to 10, then it can be an A2 for material. Is that okay? Now, if a material is more than 35% have passed this number, sieve number 200, then the material is what? A fine grained material. Is that okay? Now for this fine grained material also has A1, A4, A5, A6. So how do you differentiate this one? Also depending on the what? Both the liquid limit, and the plastic index. Is that okay? By say the plastic index, if I can remember, is equal to liquid limit minus the plastic limit. So is the measure amount of volume which you require for a material to move from being a plastic material to a material water which to reach a boundary at which it will just flow under its own weight. Is that okay? So it's amount for the more the material can take, the weaker it becomes. So if you remember our equation, we say that effective is equal to total minus water pressure. Is that okay? So the more water a material can carry, the bigger the PI, the weaker the material will be. Is that okay? For instance, let us take the material A7. 7 is a very weak material. Why? Because it has a minimum PI to be 11. Okay? The minimum PI is to be 11. Now, for the amount of water percentage to its weight, it can carry, its water content it can carry is 11. It can carry more water, which reduces its strength further. So that material will be an A7 material. But if the maximum, the minimum, the maximum it can carry in terms of PI water, the difference between LL and PL is 10, and the minimum that it can carry more, the PI, the liquid limit can be more than 41. Then we can say that material is an A 5 material. So we can look at this as an example. But further, so we can still, for instance, we have a coarse grain fine grain material and a coarse. But sometimes the fine grain material, we can further use some numerical methods to further tell its properties or its property in terms of its possibility to be used as a subgrade material. So that one is a measure what we call the group index. So a group index value is appended in parentheses to the main group to provide a measure of quality of a highway subgrade material, measure of quality of highway subgrade material. Now, if the PI is greater than 20, if it exceeds 20, as you can see here, if it exceeds 20, then the material is not good. You cannot choose it. Is that okay? A material may be an F from material, but if the PI is less, so the GI is less, this material can be improved either through can do some little bit of chemical stabilization or some mechanical. But sometimes the material is weak. If the material is weak, that it needs to be removed and replaced. If the GI exceeds what? Exceeds 20. Is that okay? So how do we do that? For instance, for GI is equal to F, this is percentage passing sieve number 200 minus 35. And then this is you know it is plastic. So it's liquid limit. Then this is the plastic index. So it's by substituting from this equation, then you can determine your GI. So here is measured the number of to the nearest of 5. For instance, if it's 2.4, so to the nearest whole number, is that okay? If it is 2.4, then we take it as a 2. If it is a 2.5, we take it as a 3. Is that okay? Take it as a 3. So we don't put it in terms of the small places. So we round off. Is that okay? We round off either we round up like here to 3, or we round down if the next digit is less than 5 to 2. So let us look at an example. So we have two materials. So we have materials A, material B. Is that okay? So we have seen that material A, it had a liquid limit and what? And the plus now for its PI, if you subtract the 2, will be 8. The plus index here for material A is equal to 8. While for B is non-plastic. Is that okay? Now for if it's non-plastic, I said if a material is non-plastic, according to our table here, this material is what? Is nearing to be an A, but we shall see. Okay, we shall see as we move forward how do we group. So let's start with material A. So material A, if I think to identify the percentage passing sieve number 0.075 millimeter. Is that okay? So if you look at this material, now for these are log scale. Is that okay? So log scale, each of these vertical lines stands for 1. This is 1, and this is 0.02, 0.03, up to 0.07. This is 8, 9, and this is 1. So this 7.5, a half of it in between, you can go and cross this line. And where it meets this line, then you come to the horizontal. We do an horizontal line. But this is about 88, you can see. Now for percentage passing, for material A is what? Is 88. So when you come back, if you come here from this table, so that step 1, determine the percentage passing sieve number 200. For material A, it is 88. The sieve number. Now for 88 is greater than 37%. Therefore, this is a fine grained what? Material. Now let's go to material B. So material B, if you go the same way, it is about, you can say, okay, actually it is here, it is 20%. So for material B, you can say that material B is 20%. Now for which is 35%, which is less than 35%. Now for this material is a coarse grained material. So we can say material A is a Celtic clay material according to this condition here, more than. Now, then material B is a Gronier material, a coarse grained material, less than. That's the first step. The second step is now to name it. To name the material. Step 2. So we can get our percentage. We get other sieves. Remember, you have sieve number 10, sieve number 40, and sieve number 200. Is that okay? For material A, we have already said it's a fine grained material. Okay, that our purpose now should be material B, which is a coarse grained material. To meet all these three conditions of this sieve, now for material A, percentage passing sieve number 10. Sorry, percentage passing of sieve number 10. Sieve number 10 is 2 millimeters. 2 millimeters. So this is 1, this is 2. So material B, 2 millimeter will give you about 70%. So I say it is 70%. Then sieve number 40, which is 0.425. 0.4. This is 0, 1, 2. This is 1, 2, 3, 4. 2, 5 somewhere here like this. So which will give us about 40% of sieve B. So we come here, it will give you about 40%. Is okay? Then what about sieve number? This one we said it is 20. Is that okay? Then liquid limit and it's non-plastic. Now let us look at this condition. Now which material is this? It's non-plastic. Let's go to our table. So we say that percentage passing sieve number, the maximum is what? The maximum for an A3 material, although it is non-plastic, although it's non-plastic, but let's take this condition. Now for the maximum here should be 10%, but here it is what? 20%. As you can see, it is 20%. Therefore, 20% is more than 10%, isn't it? Therefore, this material, it cannot be this material. Is that okay? Then let's go to A1B. This is enough. It's enough. This one disqualifies this material. Then we remain with material A1B, because the maximum is 25. On the other side we have what? 20. Therefore it qualifies. 20 is below 25. While 20 is not below 15, and also 20 is not below 10. Is that okay? Then there's condition 1. This one qualifies. Condition 1 qualifies. Then let's go to condition 2. Sieve number 40. Sieve number 40, they say we have what did we have? We have 70. Is that okay? We have 40%. 40. When you come to this material, you can see that it is maximum is 50. 40 is less than 15. Therefore, this one qualifies. Is that okay? So basing on those two conditions, these two conditions. Now for them, you can see that the material B is an A1B material. As you can see that material B is an A1B material of non-plastic. Is that okay? It's PI less than 6. Is that okay? Now for material is an A1B material. So what about material A now? Let's go to material A. Material A, we have determined that it's so defined good material. So what matters is the PI and the liquid limit. Is that okay? The PI and the liquid limit. So for this one I'll look at. So this is a condition. So the minimum. So this is the minimum, which is this one passes. Remember it is 88 passing. This is 36. Remember it is 88 passing. This one passing and this one they all pass. Therefore it is a can be enough for all these ones to pass. Now we come to these other conditions. So here it is 40, the liquid limit, the maximum. And this one our liquid limit was 26. Therefore this one qualifies. This one doesn't qualify because it's a minimum. This is maximum. This one also qualifies. So now we have A4 and A6. Then we come at PI. Our PI is 8. Okay? So 8 maximum. Remember you have this and this. Yeah, this one doesn't, because you say 8 which is less than what? 10. 10 is the maximum here, 11. But our 8 is less than 11. Therefore this one disqualifies. This one passes. Therefore our material remains, all these ones are ticks. So we can now our material is an F4 material. So when we come here, we shall say our material is an F4 material. But also we need to calculate our GI. Okay? We need to calculate our GI. So this is what we did. So we went and you see that they substituted our F. This is our percentage you substitute in this question. Our F is 88 minus 35. We can see which we can start from here. Then the rest are unknown. Is that okay? Liquid limit is 26. Then our PI is what? PI is 8. And this is also 88. So by substituting get our GI. So therefore it is a material, and this GI is less than what? It's less than 20. So our material may not be good enough, but it can be improved to be used as what? A sub-base, so a subgrade material for material So decide which material is now for the obviously the better material is material B. Soil A is fair to poor, but soil B is then a preferable material. So that is what we call the CASA and the Dashto classification system. But also we can look at another classification system which normally the Casagrande extended. The Casagrande extended is it uses what we call a prefix. Prefix stands for the major size. Is that okay? Then the surface describes the behavior in terms of is it well graded or poorly graded or well graded with excessive fines. But as you know that the first thing is to differentiate between a coarse grained material and a fine grained material. Is that okay? So if I can recall, I said that this material, for this one we were using sieve number, we're using 35% passing. But for Casagrande, use 50% passing, sieve number 200 or 0.75 millimeter. So for material which has more than 50% retained or less than 50% passing, sieve number 200 or 0.75 micrometer, 0.75, then that material, if less than 50% pass this sieve, that sieve may be, that material becomes a coarse grained. And if it's more than, then it's fine grain. Now for our purpose, now we are finished coarse. Then our purpose is to now, if it's coarse grain, our purpose is to tell between G and S. Between G and S. Is that okay? So between G and S, then we'll go to sieve number 10, 2 millimeters. Is that okay? So you find a portion. If you remember our graph, we can draw our. So if we can move very fast and look at what we discussed previously. This graph, is that okay? So for instance, if you are this point here at 2 millimeters, this is a 2 millimeters. Is that okay? So we have seen our material is coarse grained, it's gravel. So you come at this a boundary sieve. Okay? You come and plot. Is that okay? Then you determine the fraction of sand, of gravel and sand. If the fraction of gravel, that is, look at the mass. You come here. If this is x1, percentage passing. If this is x1. Now, what is the sand gravel? The sand. Now, if now the total passing should be 100. This is 100 minus x1. Will it give you? Will it give you my gravel? The gravel fraction. The gravel fraction. Then you come to 0.75. And this is we said less than 50. Now for this be our x2. X2. So now you want to get the sand fraction. The sand fraction will be equal to x1 minus x2. Is that okay? So now if we get this sand fraction. Now if this is more than this is gravel fraction, this is a sand fraction or portion. Is that okay? The gravel. Now for the percentage which passes here, it will be the sand, the silt and what? Silt and clay fraction or portion. So if this portion here of sand is greater than this, then we go and we call it a what? We call it a S, sand. We call it, go back to our table down here, we call it a sand. If now we call it a sand, if this fraction which is 100 minus x1 is greater than x1 minus x2, then this one becomes what? A gravel G. Then to tell if it's well graded, poorly or uniformly graded, look at the shape of the graph. Is that okay? So the suffix wasn't well determined. Is that okay? So we have so many conditions here. Say well graded with excessive, with some clay, well graded with excessive fine. So this was not as clear. Is that okay? So now for this was improved further in another system. Now if more than 50% passed sieve number 200 or 0.075, then that material, as we said, it was what? That material is fine grained material. So how do you tell MCO? Then you come to what we call the Casagrande chart. Is that okay? So you plot. You plot your plastic index against the liquid limit. Is that okay? So the liquid limit and the plastic enough you plot enough. If you plot these two values of plastic index and liquid limit, and if it falls within this range here, it is an M, overall plasticity, which will be an ML. Is that okay? Be a so-called an ML, or it can be this other side. Or you can, if our it has liquid, it has a high liquid limit and a high plastic index, then the material will be what? It will be CH, which means that clay of high plasticity. Clay of high plasticity. Or it will be here it will be silt of high plasticity. So you can use the Casagrande to tell MC and O. Is that okay? Using the Casagrande, it's still to tell is it LL. If the liquid limit is less than 35, it will be high. If it is between 35 and 50, it will be an intermediate. It will be an MI. It can be an CH, meaning that it is where LL, liquid limit